Okay, so now we're going to look at a different type of exponential function. It's called exponential decay. Okay, the word decay we use in language often when dead material is breaking down. So decay refers to things going down. Okay, and there's two ways we can see numbers going down with exponential functions. Okay, the first one is when our value here of, if we think back to the coronavirus, if our R number is less than 1. Okay, means in terms of the virus that if you have 10 people, they pass it on to less than 10 people, so the next day there are 9 or 8 people, so the values are going down. Okay, so when this value is less than 1, we will get exponential decay. Okay, obviously the smaller that number is, the smaller that drop in values will happen. Okay, so we're going in the domain from 0 to 7. We're going to model it over 1 week. So we're going to say on day 1, if there was 1 person infected, we have output of 1. Okay, that's on day 0, sorry. Okay, we have a power of 0, and we remember that anything to the power of 0 is 1. Okay, and our output is 1. On day 1, we have 0.9 to the power of 1, which is 0.9, and 1 times that is 0.9. On day 2, we have 0.9 squared, which is 0.81, so that value is falling. On day 3, 0.9 by itself 3 times gives 0.729, so again the value is falling, falling. When you get to day 7, 0.9 to the power of 7 is 0.478, so the values are getting smaller and smaller. Of course, this is based on 1 person on day 0. If you had 100 people, then by the end of the week we'd be down to 47.8 people. Okay, so the numbers are going down, and the total, while it's growing at a slower rate. Okay, so the total starts at 1 and it's growing but slows down growing. What does that look like on a graph? Okay, the orange line is the daily cases, and you can see that it's falling. Okay, it's falling, and it's falling exponentially, and the total, while it's still rising, it's not now going up in this fashion, it's going up in this fashion, and that's what they talked about in the news all the time, about flattening the curve. Okay, flattening the curve, slowing down the growth rate. Now, here's another example for exponential decay, and it's a common example given, and it is to do with radioactive material. So there's many types of radioactive material, and what happens with it is, to describe its radioactivity, its half-life is measured. Now, the half-life of radioactive material is the time it takes for half of the atoms in the lump of material to decay. And what does that mean? Decay means that it releases its radioactive energy, and then it goes on to be something else less harmful. Okay, so some materials have half-lives of micro or milliseconds, really fast. Okay, and others have half-lives of many years. Okay, and in this example, the half-life of radium-224 is 3.66 days. So after 3.66 days, half of it will have decayed. Okay. How much of a 0.2 gram sample is left after 7.32 decays? So first we have to connect what's 3.66 days in relation to 7.32 days. Well, basically it's 2 times 3.66, isn't it? Okay, and you would check that with your calculator. So it's asking how much of a 0.2 gram sample is left after 2 half-lives. So here's my table. Okay, instead of using those decimal numbers, I've measured it in half-lives. So at time 0, we have 0.2 grams, and I've used f of h being a half-life. So after 0 half-lives, we have 0.2 grams. Okay, now what happens after 1 half-life? Well, we need to get half of the original amount. After 1 half-life, so multiply by a half, or divide by 2 if you wish, and we get 0.1 grams. Okay, now I've just translated this into powers or indices. So 1 half, so 1 over 2 to the power of plus 1 is the same as 2 to the power of minus 1 over 1. Okay, 2 to the power of minus 1. It means you divide by the 2 one time. Okay, so after 1 half-life we have 0.1 grams. After 2 half-lives, which is what we were asked, we would get a half of the original amount and then a half of that again. So do it twice. In index form, that's multiplied by 2 to the power of minus 2. So we go half, divide by 2, divide by 2 again, and we get 0.05 grams, and that's the answer. Okay, 0.05 grams. I've just extended the table for you to look at the numbers. So 3 half-lives, you get a half and a half and a half again, or multiply by 2 to the power of minus 3. Okay, and after 4 half-lives, you do it 4 times. Okay, or multiply by 2 to the power of minus 4. So when you have a negative power on the 2, it means decay. The numbers are going to go down. Okay, our function, to write it in this form, f of x equals a multiplied by b to the power of x. Well, our function here, our a, which is our initial value, was 0.2 grams. H, I used h to signify how many half-lives. Okay, and the amount left is a function of how many half-lives. And so if you multiply 0.2 by 2 to the power of minus the half-lives passed, then you'll get your answer. Okay, and this was a picture of that function. You can see at time 0 we have 0.2 grams, and after 1 half-life that has dropped to 0.1 grams. After 2 it's halved again to 0.05. After 3 it's halved again to 0.025, and so on. And that's a function of exponential decay. It's falling, the values are falling. And notice that it gets quite close to 0, but actually you will never ever reach 0. You keep dividing by 2, you will never get the answer of 0, but you will get very small values. Now here's an exercise for us to try together. Find the exponential function. The function graphed is exponential and has the form f of x equals ab to the power of x. Find the values of a and b. Okay, so let's have a look here. So remember, our inputs x are on the horizontal axis and the outputs, or the results, are on the vertical, f of x. Okay, there are some points marked for us and we're going to use those to help figure it out. Okay, now by far the most useful one is here. Okay, the input value for that point is x equals 0. Okay, and we can see clearly that f of 0 equals, well, what's that? It's halfway between 4 and 6, so f of 0 equals 5. Alright, so let's use this format here and do some figuring out. So I can write down that f of 0, which is a times b to the power of 0, okay, so replacing your x with 0, is 5. Okay, so working on that then, a multiplied by, now b to the power of 0, we discussed that anything to the power of 0 is 1. Okay, so a times 1 equals 5. Well, that means that a equals 5. So there we have the value of a. Okay, so you can nearly always see that one straight away. Okay, look to when x is 0 because it will simplify the power part for you to 1 and you'll figure out your a. All right, now to find out b we'll have to use one of the other points. Okay, I think stick with the positive inputs for a start if you can. Okay, we have a dot for x equals 1. So when x is 1, y is 15. Okay, so f of 1 equals 15 from the graph. All right, so let's write that down. F of 1. So when f is 1, we'd have a b to the power of 1 equals 15. Okay, so those two would be multiplied. Now, we already know what the value of a is from the first one, so we can substitute for that. So we can say 5 times b to the power of 1 equals 15. Now b to the power of 1 is just itself b, so we get 5b equals 15, and to solve for b we would divide both sides by 5 and we get b equals 3. Okay, so now I have the unknown parts of my function, and I can say that f of x equals 5 times 3 to the power of x. And we can check that with our other 2 points and see does it look right. Okay, so when x is minus 1, so we can check it, I can do f of minus 1, which is 5 times 3 to the power of minus 1. Okay, and you can do that on your calculator. All right, or it's 5 divided by 3, and it's 1.66 recurring, so 1.667, I'll just round it off. And does that look right? There's 2, there's 1, there's 2, so it's 1 and 2/3, so yeah, it's about right. Okay, if you wanted you could check for the minus 2 also. So what there you put f of minus 2 is 5 times 3 to the power of minus 2, and I get 0.5 recurring. That's what that dot on top of the 5 means. It means it repeats, so we'll just 0.556 we'll say, and that's about that. That's about right. I can't really tell from this scale, but it's about right. Okay, now let's do another one. You can see straight away that this one is a graph of exponential decay because it's falling. The function graph is exponential and has the form f of x equals ab x to the power of x. Find the values of a and b. So remember last time we said first the easiest one to work with is when x is 0, and here I can see that f of 0, the result equals 4. So let's write that down. F of 0, so a times b to the power of 0 equals 4. We said that anything to the power of 0 was 1. A times 1 equals 4, so 1a, or just a, equals 4 from that point. Okay, and now we're going to look at, pick one that's really easily read. So this is a good one because I can read it well off the graph. So is this one because it's there and there. These ones that are not on grid lines are not so good to use. Okay, so use one that you can see for sure. So we'll use when x is 1, we can see that f of 1 equals 2. So let's write that down. F of 1, so that's when you have a times b to the power of 1, the result should be 2. Okay, from the previous part we see that a is 4, b to the power of 1 is just b, and that's equal to 2, so we get 4b equals 2. Divide both sides by 2, or by 4 rather, and we get b equals 1/2, or b equals 0.5. Okay, we can write our function then. F of x equals 4 times 1/2 to the power of x. We could leave it like that, or you could use your index notation. You could say 4 times 2 to the power of minus x. So turn that half upside down, and that would work also. You can use the multiply sign, or perhaps I should have put a bracket around that. It's all the same. Now let's check it. Let's check for the f of 2. Okay, the answer should be 1, so let's try it. F of 2 equals to 4 times 2 to the minus 2. Okay, that's 1 over, you'll find out that this is 0.25. Okay, and you get 4 times a quarter. 4.25 is 1, and that was right. Okay, so you try some of that, see did you understand, and practice what you've learned.